inserted as follows. So the set of numbers is 7, 8, 1, 4, 13, 20, 2, 6 and 5. How many elements are present in the root of the tree? So normally B tree is, if the order is 5 means the key is key equal to order minus 1. In a particular node, so how many keys you can store? If there is a order is 5 means you can store 4. 1, 2, 3, 4 values you can store. Okay. So key equal to order minus 1. And whenever you are taking the element and you are inserting in the key, and this should be sorted. Okay. The first one is key equal to order minus 1, and the elements in the node, should be sorted. Okay, the elements should be sorted. Okay, so these are the 2 points you have to remember, and next you will go to the work out this problem. Okay, yes. So first it is 7. So I am inserting 7. So make it as 4 blocks. 1, 2, 3, 4. 4 values you can store because order is 5. So 7, 8. So 8 is I can insert here. And the next element is 1. 1 is I have to make it in a sorting order. So what I am doing, just I'll place 1 here, 7 here and 8 here. 1 is completed, right? And then 4. So if 4 comes, where it will go? It will go here. 1, 4, 7, 8. Okay, 4 is finished. And what is the next value is 13. So next value is 13. Just write it here. Just write it here and keep it in a sorting order. 1, 4, 7, 8, 13. Okay, we have to make it in a sorting order. Remember this. Now there is no space in this node, right? So there is no space in this node. What we have to do? We have to split into off. We have to split into off, and we have to take this element to the upper post. Okay, so we have to split and make it as the next one is 7. Okay, make it in the upper one, and 4, 7 should be in left of this node, and 4 and 1 should be left of this node, and 8 should be right of this node, right? Yes. So 13 will come where? So 13 will come here. Okay, the next one is 20. So 20 will come here. So 8, 30 and 20. And then 2. So 2 will come here. So lesser than 7, so it will come here, and it is also must be in sorted order, right? So I am writing as 1, 2, 4. This one is finished. And 6. 6 will come in this place, right? So 6, write down 6 here. And the next one is 5. 5 where it will come? It is lesser than 7, and it will come here. 1, 2, 4, 5, 6. So then in this place what you have to do? So now there is no space, right? So this 4 you have to split into off. Make this 4 in this place. Okay, and keep it in the root. Okay, so now the structure will be 7, and this 4 will come up, right? So lesser than 4, 1 and 2 element, and greater than is 5 and 6. Okay, greater than 7 is 8, 13 and 20. So this is the structure. So how many elements are now present in the root? 2 elements. How many elements are present in the root node? 4 and 7, right? So the answer is option B. So the answer is option B, that is 2 elements. So the question is, how many elements are present in the root node? So 2 elements are present in the root node. The next question is, what is the maximum number of nodes in a binary B tree of order 10? Okay, this is 10 of depth 3. Okay, consider in a first depth. Okay, 3 first depth. How many elements we can store? 9 elements, right? If their order is 10 means key will be order minus 1, right? So in a first one is 10 minus 1, that is equal to 9. In a first key you can store 9 elements, okay? And the next one is, after that you have 10 splitting, right? So 10. So on every node consisting of 9 elements. This 10 nodes consisting of 9 elements, right? So 10 into 9, this is depth 1, and depth 2, 10 into again another 10. So 10 into 10 into 9, and another is 10 into 10 into 10 into 9. So what happened? 9,990 plus 9. So this one is depth 0, and this one is depth 1, and this one is depth 2. Okay, so this one is depth 3 value. So now how many elements are there? 9,999 elements. So option C is the correct answer. 9,999. What is the maximum number of nodes in a B tree of order 10 of depth 3? Depth 3. Depth means, see how many, this one is depth 1. Okay, if there is, this one is depth 2, and one more is depth 3. Okay, this one is depth 0. Yes. The next question is, a binary tree with 27 nodes as dash null branches. Okay, so n plus 1 null branches, that is 27 plus 1, that is equal to 28 null branches as per the rule, but there are no 28 values, so we are choosing the option none of the above. Okay, yes. The next question is, the time complexity to build a heap of n elements. To build a heap of n elements is, so the heap of n elements is n into log n. Okay, so n won't come, so log n won't come. So for the skewed tree only O of n will happen. O of n log n. Remember, the time complexity to build a heap of n elements is O of n log n. The next question is, the linear probing suffers from problem known as. Linear probing means what? So whenever I am doing hashing, if there is a 94th location, the value, okay, so mod 100, so 594 mod 100, so that is 94. So I will save this 594th value in a 94 location, right? If the data is already occupied with some other cell, I am switching to the next location. That is called linear probing. Okay, so that is nothing but primary clustering at the initially. Okay, linear probing suffers from the problem known as primary clustering. At the initially I have a collision with this location, right? So that's called as a primary clustering. Secondary clustering will be happen quadratic probing. Linear probing suffers from the problem known as primary clustering, and quadratic probing suffers from the problem secondary clustering. Yes. The next question is, which of the following can be sequence of node examined in a binary search tree while search for key 88? So which is the sequence? They're asking, is this sequence is possible while you are searching in a binary search tree? Okay, so is this sequence, okay, that is always the binary search tree. What is the rules for the binary search tree? Left side should be less than the root value and the right side should be greater than the root value, right? So here you have to check if you are examining these values, whether it is coming properly or not. For that, to identify this, you just draw the tree. Okay, you just draw the tree. 90. Okay, so first one A, draw this 90. Okay, so 40. 40 means what? Less than. Okay, 40. The next one is 65, greater than 40, right? So I am writing 65 here. And 50, and that will is less than 65. And this is 88. This should be greater than 50. Okay. So just now you observe this. Is this sequence is possible? Observe this. Is this kind of structure is possible in a binary search tree? See, the 40 is less than 90, correct. Okay, 65 is greater than 40 and less than 90. This is also correct. And 50 greater than, and this one also correct. Okay, when you compare this 88, see 65, the the left subtree must be less than 65, right? Less than 65, but here it is 88. So this is called violation. This is called violating the rule. So this sequence is not possible. Okay, this sequence is not possible. 88, it should be less than 65, right? But here it is a greater value. So this is not possible. So option A is wrong. Now you check it with the same thing with option B. Okay, so just write down 90. Okay, greater than 110 and less than, okay, 80. See, here itself we can identify 90, then 110 and 80. The right subtree must be what? The right subtree must be greater than, so this is the right subtree of 90. This is the right subtree of 90. So 80 should not come in the right place of 90, right? So this is again violation. So violating the rule. So option B is also wrong, right? And now check the sequence C. So check the sequence C. 190 and this one is 60 and 90 and 85, okay, and 88. So is there any violating rule? So 190 less than 60, correct, and 60 greater than 90, and 190 less than 90. 90 is less than 190. 85 is also less than 190 and 80, and this should be greater than here. Okay, so if you see, there is no violation is happening between the subtree. So option C is the correct answer. Okay, so when you check out with option D, what happens? 65, 140 and 80 and 70 and 88. See, 80, the left side, left subtree must be less than, right? Left subtree, this is the left subtree of 80. This should be less than this root node, right? So, but here 88 is greater than 80. So, this is a violation. So, option D is also wrong, right? Yes. So, option C is the correct answer. The next question is, the dynamic allocation of storage areas with WISUM files is accomplished by, WISUM is a virtual storage access method. This is a high performance access method in mainframe system. So how it works, this storage access method is, it is based on the control splits. Okay, it is maintaining in a control splits. Okay, record 1, record 2, record 3, record 4. So everything have some splitting between the records, so that I can go directly to a particular file and access it very fastly. So it is accessed, which is accomplished by control splits. The dynamic allocation of storage area with WISUM files is accomplished by control splits. And the next question is, the number of different trees with 8 nodes. the number of different trees with 8 nodes. The formula is 2 power n minus n. Okay. So n is number of nodes, where n is number of nodes. So 2 power 8 minus 8. So 2, 4, 8, 16, 32, 64, 128, 256. So 256 minus 8, that is equal to 248 is the answer. So option C, 248. Number of different trees with 8 nodes. The next question is, given a binary tree whose in-order and pre-order traversal. So they are given in-order and pre-order traversal. Based on that, we have to find out which one is post-order. Okay. So pre-order, first note down it. E, I, C, F, B, G, D, J, H, K. So this is in order, right? And this is pre-order. B, C, E, I, F, D, G, H, J, K. Okay. So what is the rules for pre-order? Root, left, right. So the root value should be come in first place, right? Okay. So B is the root. So B is the root. And in order, what is the rules? Left, root and right. Okay. So the B, where B is present? So here. Okay. So this is the left subtree and this will be in a right subtree. So now just draw B is the root and the left subtree will come E or C or F elements. And in a right subtree G, D, J, H, K. Right? So keep it as it is. Okay. So normally for a post order, left, right and root will be at the last. So the last element must be B. Okay. Here it is H. So you can remove the option D. Okay. And they told that I, E, F, C, which is common in all the three. So have it. Okay. Now you check this, this right hand side. Okay. So G, D, J, H, K. So remove this. E, C, E, I, F. Okay. So this is left subtree and this will be in the right subtree. Now you see in a pre-order, root will come in the first. In a pre-order, root will come in the first. So now you see D where it is present. So D here. So you can write D here and the left is G and the right one is J, H, K. Okay, I identified by using a pre-order and based on order. So D will become in the root. So the root where it is present here. So the left of the root is as per the in order, left, root and right. Right. So G I am giving here G, D will be root and J, H, K. Okay, this one is finished. Now you observe the J, H, K. So H is the root. Okay, H is the root and J is the left and K is the right. So now you can draw this J, H, K as, how you can draw this? J. So H is the root and J is in the left and K is in the right. Okay. So this I identified and similarly you can also identify EICF. So EICF. So C is the root and after B, C is the root. So I can write C here. E is in the left. So left, root and right. Right. So I can write E here and CF. Yes. So when you compare this, this side EICF, So EICF and here CEIF. Okay. So in a pre-order, root will come first. Okay. C will come first. So where is C in order? Here. So this must be in a left subtree and this must be in a right subtree. So EI will come under the left subtree and F will be in the right tree. And EI. So now you compare this only EI with the pre-order and in-order. So E is the root. Okay, in a pre-order, E will come first. So E is the root. And here, E is coming first and I is coming second. So it will be right. Okay, right of I. Because the left root right. So I will come in the right of the E. Okay. So I'm just erasing. So in the right side I will come. So just join this B. Okay. So just you draw this. Okay. You will get the binary tree. Okay. Now you get the binary tree. In this binary tree you have to do the post order traversal. So what is post order? Left, right and root. So what is left subtree? So first I am coming to the left subtree and here what is left subtree? This. And here in this root node I am coming. So left nothing is there and so first one is I and then E. I, E, okay, left, right, root. And then similarly left, right, F and then C. Then coming to the right side. So left first. So G. So the right on G and right side. So right side is again a tree. Again follow left, right, root. J, K, H. So J, K, H and then finished D and then last post order. So left side and all completed, right side completed and then root. So the answer is I, E, F, C, G, J, K, H, D, B. So I, E, F, C, G, J, K. So option A is the correct answer. I, E, F, C, G, J, K, H, D, B is the correct answer. The next question is the number of disk access performed by insertion operation in B tree of height H. So height H is, so I have to traverse O of H. Okay, the number of disk access performed by insertion operation. So insertion operation means I have to search. Okay, so I have to search all the height, right? If there is height 1 or 2, have to search all the height, right? So O of H time it will take. The next question is when the priority queue is presented by max heap, the insertion and deletion of an element can be performed. So insertion max heap. So the insertion will happen O of, so normally max heap is called as it's a binary tree. So so whatever, if I want to insert this element or if I want to delete this element, my maximum complexity is O of log n, right? So O of log n is the time complexity for insertion and deletion of an element. So here there is no such option. So I am choosing D, none of the above is the option. The next question is the post order traversal of a binary tree is D, E, B, F, C. This is a post order. They are asking find out the pre-order traversal. Okay. So using only one sequence we cannot able to find out normally, but we can we just compare this like this. We have to just write it like this, A, B, C, D, E, F and just to see whether it is coming or not. So if you like write generally A, B, C and D, E, F, you can see the post order is DEB and FCA, right? So using this you can find out pre-order. Pre-order means what? Root, left, right. So root is A, and again root is B and D and E. Okay, this one is finished, and then come again here C, F. So A, B, D, E, C, F. Option C is the correct answer. Okay. Actually, in this question, they have to give two values. We are just guessing and write it down. Okay. The next question. Yes, the next question is B plus tree or preferred to binary tree in database. So, because of disk access is much slower than memory access. Disk access is slower than memory access. So, this is the answer. Check it out. A hash table has space for 75 records. Then the probability of collision before the table is 6% full. So 6% is full. Okay. Hash table has a space for 75 records. Okay. Totally 75 records space is there. Then the probability of collision before the table is 6% full. So 6% full, that means 6% of 75. Okay, so 6% of 75 is 3, 4, so 18 divided by 4, that is equal to 4 4s are 16.25. So normally 5. So normally 5 records. So we need to insert 5 records to make it as if the collision. Okay, so for example 1 by 75. If there is a one record is there, and what is the collision? For 75 records, if 1 is there, what is the collision? And for 2 by 75, and if it is 3 by 75, and what is the probability for 4 by 75 plus 5 by 75? If you add all these things, 3 plus, so denominator is same, I am adding all those things in the upper numerator. So 5 plus 4, 9, 9 plus 10, 15. So 15 divided by 75, that is equal to, so 3 divided by 1 5s are 5, 5 5s are 25. So that is equal to 1 by 5. That is equal to 1 by 5 is nothing. It is when you multiply by 100, it is 20%. Okay. So 20%, that is can be represented as 0.20. So probability of collision before the table is 6% full is 0.20. The next question is, which of the following data structure is non-linear type? Linear type means the same kind of thing. Non-linear type is graph, trees and structure. So graph, trees, list is also a linear type, stack and string. So everything is a linear data type. Non-linear will come under graph, and tree data structures will become under non-linear data type. So D option, none of the above is the answer. The next one is the total number of comparison in a bubble sort. The total number of comparison in bubble sort is O of n square, because every element is compared with an adjacent element. So it will take O of n square. So here there is no options for n square. I am choosing a none of the above is the answer. The next question is, which of the following is a bad example of recursion? So factorial and tower of Hanoi, tree traversal, which are all good examples for recursion. As per in the book, they told that Fibonacci series is the bad example. Okay, this is a bad example for recursion, Fibonacci series, because we are initializing at the start, right, 0 and 1, and then we are doing in a recursive manner. So Fibonacci series is called as a bad example of recursion. The next one is the number of nodes in a complete binary tree of height with roots at level 0. So what is complete binary tree? So every node consists of 0 or 2. So this is a complete binary tree. So this is 2 to the power 0. This is 2 to the power 1. This is 2 to the power 2. So for example, in a root node you have one node, and then because as it is says that complete binary tree, here you have every child as every root as 2 child, okay, except the leaf node. So here you have a 2, and then here you have a 2. So 2 power 0, 2 power 1, 2 power 2 up to height how much? If there are 5 means 2 power h. So you can say that number of nodes in a complete binary tree of height h is equal to 2 to the power of 0 plus 2 to the power 1, 2 to the power 2 up to dot 2 power h is the answer, right? The next question is the postfix expression AB plus CD minus star can be evaluated. So evaluating the expression or postfix expression that can be done using the stack data structure. It's not tree or queue or linked list. So recursion, the applications of stack, you know, the applications of stack, evaluating the expression, or postfix expression. We are using stack data structure. The next question is the post order traversal of a binary tree is the same question repeated. Okay, so we have already seen this. They didn't give the pre-order, so actually we are not able to find out with only one order traversal. We need any 2 order traversal so that we can find out the another one. So we have only one order, this one, post order traversal. So based on this we cannot identify, but we can guess it. Okay, we are just guessing this A, B, C, D, E, F. So generally we are writing like this, then we are searching the pre-order. So A, B, and then root left, right. So root left, right, as per this it is the pre-order traversal. Root left, right. Okay. The next question is a binary search tree is a binary tree, so which is all items in the left subtree or less than the root. Correct. All items in the right subtree are greater than or equal to the root. So this is also correct. Each subtree is itself a binary search tree. This is very correct. Each subtree itself for example 5. So 4, okay, 3, here it is 2, and for example, so you consider this one as 7, okay. So here you have a 5. See, they are telling that each subtree is itself a binary search tree. This is a subtree, okay. So all the elements in the left subtree must be less than the root 7, okay, less than 7, 4, 2, 5, all the elements are less than 7. And similarly, this subtree is itself a binary search tree, okay, this subtree 4, 2, 5. See, left is lesser than the root node. Here 4 is the root, 2 is the less than 4, and 5 is greater than 4. So each subtree is itself a binary search tree. So this is also correct. So option D, all of the above is the answer. The next question is what deletes the entire file except the file structure. So zap is the command which deletes the entire file except the file structure. Okay, so this is also done fast. The next question is a transaction manager is which of the following? The transaction manager in a database, he maintains a log of transaction, he maintains before and after database images, and also the transaction manager maintains appropriate concurrency control. If you want to data to read or write, so this is to avoid the concurrency problem. So that also maintained by the transaction manager. So he maintains a log of transaction, maintains before and after database images, maintain appropriate concurrency control. So all of the above is the answer. The next question is leaves of which of the following trees are at the same level? So AVL tree which will be differ by 1. So you can remove that. So expression tree also differ. Okay. Binary tree is also when you see as an what a left curved tree and right curved tree, so the leaves won't be at the same level. But in a B tree, the leaves are at the same level. Okay. So in a B tree, all the leaves are at the same level. All the leaf nodes should be at the same level, which will be the definition we have to remember for a B tree. All leaf nodes should be at the same level. Every node except for root and leaves at least m by 2 child. So this is the just 2 points you have to remember. Okay. The next question is, the in-order traversal of the tree will yield a sorted listing of elements of tree in binary search tree. Whenever you are having the binary search tree, if you do an in-order traversal, you will get all the elements in a sorted manner. Okay, that is binary search tree. What is the difference between binary tree and binary search tree? Binary tree means you just have any 2 elements. Okay, that is binary tree. Either it is left subtree, left screwed and right screwed, anything. But binary search tree means always the root, and in the left side always it should be lesser than, and in the right side always it is greater than element. Okay, so if you traverse this in an in-order traversal, left, root and right, if you traverse this binary, this is a binary search tree, if you traverse this binary search tree in an in-order manner, you will get the sorted listing of elements. You will get the sorted list of elements in a tree. So option B is the correct answer. The next question is, to represent hierarchical relationship between the elements, which data structure is suitable? So here it is missing the option C. It is nothing but tree data structure. The hierarchical relationship is it is presented with tree data structure. With tree data structure. Okay. The hierarchical means 1, and then here you have a 2 and 3, and then like this. So this is tree data structure. The hierarchical relationship between the data elements is always present with the tree data structure. The next question is, consider a weighted undirected graph with a positive edge weight and let u, v be an edge in the graph. It is known that shortest path from source vertex S to u as weight 53. Okay. So consider a weighted undirected graph with a positive edge weight and let u, v be an edge in the graph. So u, v, consider this one as u, v is an edge in the graph. It is known that the shortest path from source vertex, consider this one as source vertex, that is S to u. So S to u is weight 53, and the shortest path from S to v. So shortest path from S to v is 65. So which statement is always true? Which statement is always true? So here it is 53 and this one S to V is 65. So weight of u, v. So weight of u, v is always greater than or equal to. So 53, if you add, this will become, so this is the shortest path means, so 53, 65 minus 53 equal to 12. So if I said from S to V, this is the shortest path, that is 65 is the shortest path. If I choose this one as the shortest path, and this path from S to U and U to V must be equal to or greater than 12. Okay, if it is greater than 12, so that I am choosing S to V. Right. So the weight of u, v should be greater than or equal to 12, which is option C. The next question is, number of binary trees formed with 5 nodes. 5 nodes, n equal to 5. So 2 power n minus n is the formula for find out the number of binary trees. So 2 power 5 minus 5. 2 power 5 is 30. 2 power 5, 16, 32, right? 2 power n plus n, I think. So the number of the number of binary trees formed with 5 nodes. Number of binary tree formula is 2n divided by n plus 1. Okay, so 2n, in the place of n you have to substitute 5. So 2 5 c 5 divided by n plus 1, 5 plus 1 6. Okay, so 10c5 divided by 6. We have to identify NCR factorial equal to n factorial divided by r factorial n minus r factorial. So that is equal to 10 divided by 5 factorial into 5 factorial. So now you can write this 5 factorial and this 5 and the above 5 factorial will be cancelled, right? So 6, 7, 8, 9 and 10, and then here this 5 factorial, 1 into 2 into 3 into 4 into 5. So 5, 2, 10, this will be cancelled, and 3, 4, this will be cancelled, and this will come 2 times. So 4, so 4 9s are 36, 36 divided 36 into 7, this is this 10c5 answer is 36 into 7. So if you this 6 is there, right? So 6 6 are 36. So 6 into 7, it is nothing but 42. So option D is the correct answer. Number of binary tree formed with 5 nodes is 42. So when you apply 2n cn divided by n plus 1, you apply this value, so you will get the 42 answer. And you have to remember this NCR formula. NCR equal to n factorial divided by r factorial into n minus r factorial. And the next question is, the following postfix expression is evaluated using a stack. So this expression is evaluated using the stack. So what is the rules for this? Whenever operand is entered, the rules for this is operand. Okay, operand, when operand encounter, push into the stack. When operand encounters, push into the stack. Okay, just remember these 3 points. You can easily execute the evaluation using stack. Whenever any operand is encountered, we have to push it into the stack. And whenever an operator is encountered, you have to pop top 2 elements. Operator encounters, whenever operator encounters, pop top 2 elements. Pop top 2 elements, pop top 2 elements in the stack, and execute evaluate B operator A. Okay, so whatever operator is coming, we have to evaluate B and A. A is the topmost element and B is the next topmost element. Okay, so remember this is very important. A is the topmost element and B is the next element, that is below. Okay, for example, you can see here, and again push into the stack. So this is the push into the stack. The evaluated value will be push into the stack. Okay, so this is the only 3 points you have to remember. We can write many number of expression, we can evaluate it. Whenever an operand encounters, push into the stack. Whenever an operator encounter, pop top 2 elements from the stack and evaluate B operator A, and then push the evaluated value again into the stack. Okay, so see here, first 8 is encountered, so 8 push into the stack, and 2 and then 3. So and then what it encounters? This power. So power is encountered. So whenever an operator encounters, pop top 2 elements. So this is A and this is B. But they are telling that as per the rules, B operator A. So I am evaluating 2 power 3. So 2 power 3, that is equal to 8. 2 to the 4 and 2 to the 8. Again push into the stack. Okay, so 8, then again 8. So what happens? And then slash encounters. Slash is coming. Okay, so slash is 8 divided by 8, that is equal to 1. So again push into the stack. So I am writing here 1. And again 2 encounters, again 3 encounters, and then star. Star means B evaluative OR. So what happens when star evaluates? 2 into 3, 6. So 1, 6. So what is the top 2 elements of the stack after first star is evaluated? So this is the first star, this is the second star. So you can stop the process from here itself. whenever the top two elements of the stack after first star is evaluated, so this is the first star, at that time what is the top two elements in the stack? 6, 1. So 6, 1, option A is the correct answer. Okay. So they are asking only top two elements. This is the top element. Okay. 6 is the top element and the 1 is the next to the top element. The next question is the upper bound of computing time of M coloring decision problem. M coloring decision problem is, that is O of n m to the power n. The next question is the worst case time complexity of AVL tree is better in comparison to binary search tree. So the worst case time complexity of AVL tree is better in comparison to binary search tree for search, insert and delete operation. So when you are comparing binary search tree, AVL tree is best in searching and inserting and deleting operation. So why AVL tree is better in comparison to binary search tree? Because AVL tree will be balance itself. Okay. So AVL tree is balance itself, that is the balance factor is always 0, it will balance already. Okay, we have seen, right? The balance factor should be 0, 1, 1, minus 1. And if the length is long, in a binary search tree it won't do that, but in a AVL tree it will balance itself. Balance itself. AVL tree makes balance itself. So search, insert, deletion operations is in a worst case time complexity also better than BST. Right? Yes. The next question is a hash function f is defined as f of key. This is the hash function f of key equal to key mod 13 with linear probing. So this is a linear probing. If the particular element is not fulfilled, if the particular memory location is filled, means I will search the next location. That's called linear probing. Is used to insert keys this. What will be the location of 79? So first I will take 55. So 55 mod 13. So the remainder is 4 3s are 12, 52. Remainder is 3. 58 mod 13. That is equal to 6 3s are no 5. So 58 mod 13, that is equal to location 6. So mod the remainder value is 6 and 68 mod 13 equal to 0. Okay, and then 91 mod 13. 91 is 7 3s are 21. So the remainder is 0 only. 91 mod 13, 7 3s are 21. So 19. So remainder is 0. And then 27 mod 13, that is equal to 2 3s are 26. The remainder is 1. And 145 mod 13, that is equal to 1 13s are 13 and 115. So the remainder is 2, right? What will be the location of 79? So 79 mod 13. So 6 3s are 78. Okay. 6 13s are 68 and 7. So 6. So 11 is the answer. 11 is the location. What will be the location of So 68 mod 13 is 3. Okay, sorry for the mistake. Just make it correct. So 55 mod 13 equal to 3. Okay, 4 3s are 52. Okay, 4 13s are 52. Remainder is 3. And 58 mod 13 equal to 6. And 68 mod 13 equal to 3. Okay, 5 13s are 65 and the remainder is 3. And 91 mod 13 equal to 0. 27 mod 13 equal to 1. 145 mod 13 equal to 145 mod 13. Okay, 1 13s are 13, remainder 15, right? 1 13s are 13 and the remainder is 2, right? So 2 is the remainder. And after, what will be the location of 79? So if you divide 6 13s are 78, the remainder is 1. So now you place as per the reminder from the start. So from 55 I am placing in the third location. Okay, 55 I am placing in the 0, 1, 2, third location. 55. Okay, 58 I am placed in a sixth location. 0, 1, 2, 0, 1, 2, 3, 4, 5. This is sixth location. 58. And 68 mod 13 equal to 3. Okay, which is already 55 is occupied. So what I am doing is I am searching the next, because they said that we are following linear probing, right? So 68 is stored in the fourth location, and 91 mod 13 equal to 0, so 91 will be placed here. 27 mod 13 equal to 1, so 27 will come and placed in the first location, and 145 mod 13 equal to 2, so 145 will be stored in the second location. Now here we see what is the 79 mod 13, that is in 1. So but 1 is already occupied, 2 is occupied, 3 is occupied. So 79 will be stored in the fifth location. 79 is stored in the fifth location. Okay, 79, because as per the linear probing, this all the cells are occupied. Okay, so the correct answer is option 5 is the correct answer. The number 79 is stored in the location 5. It is nothing but 89th sum. Okay. The next one is, consider the tree given below. Using the property of eccentricity of a vertex, find every vertex that is the center of the given tree. Actually, there you can have a shortcut method to find out the center of a given tree. Okay, to find the center of a given tree, those who are vertex of degree 1. Okay, this is one of the shortcut method I am using. Those vertices have the degree 1. Remove that node. Okay. For example, so after degree 1 removing in a first step, so A is having only 1 degree, right? And C is having, E is having, F is having 1 degree, and here you have 1 degree, and here you have 1 degree. Other nodes are having 2 degrees. So remove this and all. So after removing, what will you get? C, H, then I, this K, and M, and then this B, D, and G, right? So this is the second step tree. If you remove again degree 1, who are all the node have a degree 1, remove that node. So B, D, G, these have only 1 degree node, right? So remove this. Okay, are you able to understand? So this is a degree 1. Okay, this node and all have degree 1, but this have 2 degrees, right? So remove this. So now you see what is C, H. Okay, so this is the center of the given tree. C and H is the center of the given tree. Just remove degree 1 node. Okay, that's all. Repeat the step until it gets only 1. Okay, so here you have only 1 degree with C and H. So stop the process. So option, this is the center of the given tree. The next question is, the maximum number of keys stored in a B tree of order M and depth D is M power D into M minus 1. So actually this is the formula. Okay, maximum number of keys stored in a B tree, that is M power D into M minus 1. That is, you can see, right, 10 into 9 and 9 elements, and 10 into 10 into 9, right? So this is a depth, and this is M minus 1. Okay, so actually what he did is M minus 1 MD plus 1 minus 1, it became 0, right? So M power D into M minus 1. Option C is the correct answer. The next question is, what is the result of the following expression 1 and 2? So 1 and 2 you represent in a hexadecimal value 001 0010. You do it with and is 1.00000, and then 3 and 4. 3 is 0011 and 4 is 0. So do AND operator. So here it given as AND. So 1.0000. Okay. So now you add this and this. So you will get 000. Okay. So the answer will be 0. What is the result of the following expression is 0. Given an empty stack after performing push 1, push 2. So as per the instruction you do it. First they are telling push 1. So I am pushing 1, and then push 2. So I am pushing 2. Then pop. So pop means what happened? The stack will be like this. Popped element is 2. Okay. So 2 is removed from the stack, and then push 3. So 3 is pushed. So 1 will be there and 3 will be there. And then push 4, and again 2 pop instruction, pop. So 4 will be removed and 3 will be removed, right? So the top of the stack is 1, and again push 5. So I am pushing 5 again here, and then pop. Okay, so I am popping means 5 will be out. And what is the value of the top of the stack? So what is the value of top of the stack at now? So that is nothing but 1. So 1 is at the top of the stack. The next question is, the time complexity of some standard graph algorithms are given. Match each algorithm with its time complexity. Okay. Bellman-Ford algorithm is O of mn, Kruskal is O m log n, and Floyd normally n cube, and topological sorting is O of n plus 1. So that is available in option A. The next question is, let n be a function defined by t of n equal to 1, t of n equal to 2t n divided by 2 plus n. Which of the following is true? So here the option C is the correct answer. T of n equal to O of n. So this have one master theory which have a big concept. I am explained which is in the YouTube. Okay, just check it out. The next question is, which of the following permutation can be obtained in the output using a stack of size 3 elements, assuming that input is this. Okay, so they are telling that which is the possible permutation. So if I am only 3, stack size is 3. Okay, here 1, 2, 3 I inserted. So I am just popping this 3 and 2 and 1. So and again pushing 4 and 5. So if I am popping out, what will come? 3, 2, 1, and 5 will come out. Okay, 5, 4. So what is the option is 3, 2, 1 and 5, 1. This is the, you are getting the value after inputting, after you are popping the element. This is one type of permutation. Okay. The next question is the same. What is the result of the operation? That is D0. The next one is, for a B tree of height h and degree t, the total CPU time used to insert a node is O of th. So height and degree t. The next question is the time complexity to build a heap with a list of n numbers. So build a heap normally n log n. So to build a heap with list of n numbers is O of n log n in a heap set. The next one is the value of postfix expression. The value of postfix expression 834. So just push it 8, 3, 4. When plus is encounters, have to pop 2 elements. 3 plus 4, that is equal to 7. And then again minus. Okay, 8, 7 is in the stack, right? And then minus encounters. Minus means 8 minus 7, that is equal to 1. Okay, and then 3 encounters. Push into the stack 1. And then what encounters? 3 is encounters. And then 8 is encounters. And 2 is encounters. And then slash. When slash comes, this one is A and this one is B. Evaluate B operator A. So 8 divided by 2, that is equal to 4. Again push into the stack. So what happened? Now stack 1, 3 and 4. Then plus. So what happens? 3 plus 4 equal to 7. So 1 and 7. Okay. And then again star. So star encounters. 1 star 7, that is equal to 7. Okay. And then 2 encounters. And then power encounters. This is nothing but power. So 7 to the power of 2, that is equal to 49. Right. So 49, now it's the top of stack, and then it is 3. So 3 and then plus. Plus means 49 plus 3, that is equal to 52. So option D, 52 is in the, after evaluating the postfix expression, the value is 52.